such that f of g of x is equal to x, and g of f of x is also equal to x, then we can conclude that f and g are inverses of each other. So rather than saying we know two functions are inverses, so that tells us that their composition gives us x, we're saying if I take any two functions and I find their composition, if I get x, then I can conclude that the two functions are inverses, which is a little bit more useful than knowing their inverses ahead of time, because this way we can start with any two functions and we have a way to verify that they're inverses. So you'll see this question in two different ways. The first is I can say verify that f of x equals 4x minus 5 and g of x equals x plus 5 over 4 are inverses. So inverse functions. So if I word it like this, I'm basically telling you already that they're inverses, and I just want you to show me using compositions that like prove that they're inverses. So if it's worded like this, then if you take the composition and you don't get x, you should go back and try again, because I've told you already that they have to be inverses. So you're not finding out whether or not they are, you're just proving that they are by taking those compositions. So to answer this question, we would just find f of g of x and g of f of x and show that we end up with x. So f of g of x is f of whatever g is, so we'll replace g of x with x plus 5 over 4. And then f says multiply 4 times your input and subtract 5. So that 4 is really 4 over 1, right? So my 4's will cancel, and we end up with x plus 5 minus 5, which in fact is equal to x. And then we'll go the other direction. So g of f of x so we'll replace f of x with 4x minus 5. And then g says take your input, which is 4x minus 5, add 5 to it, and divide by 4. So negative 5 plus 5 is 0. So this just gives us 4x divided by 4. Those 4's cancel, and we get x. It's kind of exciting because it all works out so nicely. And that's enough to verify that two functions are inverses. If you want to at the end be like, look, they're inverses, you can say that. But one thing you can't do is just say f of g of x equals x. Like, you have to actually show that it works out to be true. Because essentially we gave you the answer here, which is that they are inverses. You're just showing us why. Does that make sense?
So on the test we can just leave it like that?
Yep. As long as you find both compositions and you end up with x. And I mean, the steps that you take to get there are true. Like, don't just write it and then write equals x at the bottom. I read the whole thing. So then the other thing we can do is ask if two functions are inverses. So the approach that you'll take is exactly the same. You'll just find the compositions. The only difference here is that the answer could be no. So if you end up not getting X when you take the composition, then you'll be like, no, they're not inverses. So we could ask, are f of X equals X over 2X plus 3 and g of X equals 2X plus 3 over X inverse functions. And this is where we have to be a little bit careful because in math, the word inverse is used in a lot of different ways. People sometimes call numbers that are opposites of each other inverses because they are additive inverses, which means that if you add them together, you get 0. People sometimes call reciprocals inverses because they are multiplicative inverses, which means if you multiply them, you get 1. But in this setting, an inverse function means it's a function that undoes another function. So it's the whole thing. So if you look at these two fractions are reciprocals of each other, which some people use the word inverse for reciprocal. And it's not incorrect, it's just that that word has a lot of different meanings. So be careful when you have something like this where you see that like, oh yeah, look, those are reciprocals of each other, so they're inverses. It's true that those fractions are multiplicative inverses of each other, but the functions aren't necessarily inverses of each other. And that's where we have to take the composition to figure it out. So we're going to say f of g of X equals, so we're taking f of, we'll replace g of X with 2X plus 3 over X. And then f says take your input, which is 2X plus 3 over X, and divide that by 2 times your input plus 3. So in order to simplify a complex fraction, remember we want to get a single fraction in the numerator and a single fraction in the denominator before we divide. So that 2 is the same as 2 over 1. So we're just multiplying by the numerator. So we get 2X plus 3 over X over 4X plus 6 over X plus, and this 3 is like 3 over 1. So to get common denominators, I'm just going to multiply it by X over X. And that gives me 2X plus 3 over X over 7X plus 6 over X. So 2X plus 3 over X divided by, now that we have a single fraction in the denominator, we'll do that division. So 7X plus 6 over X gives me 2X plus 3 over X times X over 7X plus 6. So those X's cancel, but then I end up with 2X plus 3 over 7X plus 6, and that can't be simplified anymore. And that's definitely not equal to X, right? So no, they are not inverses. And I don't have to find g of f of x, because in order for them to be inverses, both compositions have to give me x, which means if one of them doesn't, I'm not even going to bother finding the other one, because I already know that they can't be inverses. So there's no need to do that extra work. How do you guys feel about this? Do you want to do one more like this? Yeah, let's do one more. Let's say our f of x equals x over 2x plus 3, and g of x equals 3x over 1 minus 2x inverse functions. Okay, you guys try that one. So you're just finding the compositions. You're finding f of g of x, and then you're finding g of f of x. What everybody came up with? And so our answer is yes. They are inverse functions because we got x both times. Kendall, what do you think? Sorry, it got really small because I was afraid of running out of room.
It's the second to last, third to last of 3x over 2x plus 3 divided by 3 over 2x plus 3.
Yes. Uh-huh. Because... Oh, go ahead.
Oh, wait.
I said in the denominator we had
yeah.
2x minus 2x.
Yeah. Okay.
So that was 0.
I figured out what I was.
Good?
Yeah.
Okay. Okay, then the other thing we're going to do today is we're going to find inverse functions. So the first step to finding inverse functions is to check that the function you're starting with is 1-to-1, because if it's not 1-to-1, it doesn't have an inverse function. So to find a function's inverse, first we're going to graph the function to verify that it is 1-to-1. So let's do f of x equals 3 over x squared minus 6. Now when you put these into your calculator, if you don't actually have the fraction notation in your calculator and you're using like the division sign for fractions, be sure that you put your entire denominator in parentheses. So you need this, and if there's addition or subtraction in your numerator, you would also need parentheses around your numerator. So if you don't have a graphing calculator, that's okay. You can use like Desmos. We would just say it is not 1-to-1. So it doesn't have an inverse. It has an inverse relation, like all relations have inverse relations, but it does not have an inverse function, so we can't find f inverse of x as a function, at which point you just stop. So next we will, I forgot to write the instructions on the first one, so find the inverse of f of x equals let's do 4x plus 3, whoops, over 7. Can't seem to make an x here. There we go. So go ahead and graph that one. And again, be sure that since there's addition in the numerator, be sure you're putting that entire numerator. Is just going to be to replace f of x with y. And the reason we do that is just because it's easier to work with y than with f of x. So instead of writing our output as f of x, we're just writing our output as y. So we're going to write y equals 4x plus 3 over 7. And then remember yesterday, that first example we did with the contamination and pollution, like all we did was we said, okay, we're starting with something that has an input of pollution and gives us an output of contamination. And we want to end up with something that takes an input of contamination and gives an output of pollution. So we just solved that equation for P so that it was P equals something instead of C equals something. So we're going to do the same thing here. We're just going to solve the equation for our original input so that that is our new output. So that's an ugly 7. The next step is to solve for x. So since I have fractions, I'm going to clear them by multiplying both sides by 7. So that gives me 7y equals 4x plus 3. And then the key to these is once you've cleared fractions, you want to get all the terms that contain x on one side and all the terms that don't contain x on the other side. So right now I have just one term that contains x. It's on the right. So I'm going to subtract that 3 to get all the terms that don't contain x on the left. So we have 7y equals, 7y minus 3 equals 4x. And then we'll just divide both sides by 4. So 7y minus 3 over 4 equals x. And then the last step, it seems a little bit odd because we're so used to x and y being like set values. But remember that x is just the standard input we use for all functions. So we are going to rewrite this function using x as your standard input. So we're going to write f inverse of x equals whatever our function is. So really what we've done here when we solve for x is we've found the operations that you have to do with your input to undo our function. And so we're going to just write those in function form. F inverse of x equals, well, what I found is I need to multiply 7 by my input, not add, subtract 3, then divide by 4. And it doesn't matter what my input is. So all I'm doing is I'm using a standard input of x because that's the dummy input we use for all functions. And that allows us to graph both f and f inverse on the same xy coordinate plane using x as the input for both and y as the output for both. So f inverse of x is going to be 7 times my input minus 3 divided by 4. So you just don't want to get hung up on like the x's and the y's as like set things. We're just using x as the standard input once we've figured out the rule for undoing our function, which is what we have on the left side of that equation, is just a set of operations that will undo f. Does that make sense? Okay, let's do one more. Let's find the inverse of f of x equals x over x minus 5. So these are probably the most challenging ones, are the ones that have the variable in there more than once. So if you can do these, then you can pretty much do any of them. So first, let's graph that to verify that it's 1-to-1. And remember to put that x minus. So we're going to replace our f of x with y. And then we want to clear fractions, so we'll multiply both sides by x minus 5. So here my denominator cancels, and we'll distribute on the left. So we have xy minus 5y equals x. And then again, the key step in these is remembering to get all the terms that contain x on one side of the equation and all the terms that don't contain x on the other side. So I just go through and look for terms that contain x. And so in this case, I can subtract xy from both sides. So we get negative 5y equals x minus xy. And then in order to solve for x, we just want one factor of x on the left. And so we'll factor that x out as like the GCF. So we have negative 5y equals x times 1 minus y. And then we'll divide both sides by whatever it is x is being multiplied by. So in this case, we're dividing both sides by 1 minus y. We've got our x alone. So now we just have to write this in function notation. So f inverse of x equals, and remember this, the left side of this is just the rule for our inverse. So we're just going to use x as the input, which really just means replacing those y's with x's. So negative 5x over 1 minus x. And one thing about finding inverses is depending on sort of how you go about it, if you're working with somebody, you guys could get answers that look fairly different, but they really are the same. So like for instance, up where I subtracted xy from both sides, if you had added 5y to both sides and then subtracted x from both sides, you would have gotten 5x over x minus 1, which is exactly the same thing because both the top and the bottom just differ by a factor of negative 1. But they look fairly different, so don't panic if somebody gets something that looks different than yours. You can get the same thing but have it look very different. Does this make sense? Do you guys want to do one more? Let's do one more. We were, but I don't want to deprive anybody of any math time. So find the inverse f of x equals 2x over, well, no, let's do this. Let's do x plus 3 over x. Good. And if you got negative 3 over 1 minus x, that's fine too. That's exactly the same. So again, like, it might be worth writing these two things down because those are sort of the pieces that are easy to forget. And then you kind of start moving things back and forth without sort of having a goal. So when you clear fractions, that's your next step. And then you factor out your x. Feel good about it? Okay.